Okay, thank you for the introduction. So today I will present our work on the reliability of profile matching across large online social networks. So probably most of you have accounts in different social networks, and you reveal different aspects of your life in each of these social networks. For example, we can learn about someone's profession on LinkedIn, and we can learn about someone's interests on Twitter. So by matching all the profiles that users have across these different social networks, we can create a more complete image of a user. And of course, the consequences is that many parties are interested in matching users' accounts. First, we have businesses that can build new services. For example, there are already startups that match profiles to help recruiters hire people, and you can also have all these people search engines. Besides matching for businesses, there is also an opportunity for researchers that can study, for example, not only the user behavior within a single social network, but how users behave across different communities. Finally, matching profiles can also be useful for the social network themselves that can now be able to detect a duplicate or impersonating account, which is a big problem for now for them. On the other hand, matching user profiles also raises some serious privacy and security concerns for the users themselves. For example, by matching users' accounts, someone can reveal much more than they realize about themselves. Anyway, for both these opportunities and concerns, it is very important to actually understand the limits and pitfalls of matching accounts across social networks. So the precise goal of our project is to investigate the reliability of profile matching schemes across large real-world social networks, only using publicly available profile attributes. So what do I mean about the reliability? Well, a reliable matching scheme is a scheme that doesn't link the profiles of users that don't actually belong to the same person. And this is very important because neither service provider, neither users don't want their accounts to be linked to the wrong person. Then we focus on large real-world social networks where the matching scheme has a really hard job to do, and it has to select the matching profiles out of potential billions of potential matches. And finally, we focus on exploiting the information users publicly provide about themselves, such as names, screen names, location, bio, profile photo. And we are focusing on this because this is the actual information that anyone can access through internet and through APIs. So anyone can mount and do this kind of matching. So before I dive into the methodology, here's the more precise definition of our matching problem. Given one account in one social network, for example, Twitter, find a matching account in another social network, for example, Facebook. And I just want to point a slightly different than the problem of matching two graphs or the problem of entity matching that have been well studied in the data mining community. And the main reason the problem is slightly different is that we don't assume that we have access to the entire social network, to the data in both social networks. We can just view a part of it. And the reason that we focus on this particular problem is that this is what we can actually do in practice using this data. So now we are not the first who tackled this problem. And the traditional way to solve it is to reduce it to a binary classifier that given two profiles into social networks detects whether they belong to the same person or not. And for doing this, we can apply this standard machine learning algorithms. You can take some positive examples, and then you can take some negative examples, and you train some classifiers with the similarity between the names, the screen name, the location of these two profiles. Then when you want to test the accuracy of the matching scheme, you just check whether the classifier detects correctly a pair of matching profiles, in which case a true match, or if it links pairs of accounts that belong to different users, in which case you have a false match. Now, to evaluate the reliability, what we are doing is we use these precision and recall measures. So the recall, if you remember, is the fraction of matching profiles that the matching scheme actually links together. And the precision is the fraction of all pairs returned by the matching schemes that are actually true matches. Now, since we said that a reliable matching scheme doesn't have to link profiles that don't belong to the same user, what we actually mean is that the matching scheme has a very low number of false matches. So in the rest of the talk, I will consider that if a scheme has a precision that it's higher than, let's say, 95%, so 95% of the pairs of accounts that the matching scheme actually links are actually true matches. Sorry. So I was mentioning there are many studies for the past 6 years or so that propose different techniques to match profiles across social network. The good news is that most of these schemes achieve good precision and recall when they were evaluated over their data set. However, the bad news is that the matching scheme have only been tested over small sample data sets that contain some matching profiles and some randomly chosen non-matching profiles. So the problem is that it is unclear how this scheme would perform on real-world large social networks. And the reason why we believe that the results might not hold is because suppose that in Facebook there are 10 other people that are indistinguishable from my profile, so they would all be linked to my Twitter profile. Now, if you only take a sample of, let's say, 1,000 Facebook profile or 10,000 or 100,000, the probability that more than one of these profiles will end up in my sample, it's actually very low. So the precision and the recall of matching scheme over this sample data set will look as it is very good. Okay. So our goal is now to test the reliability of matching scheme in practice at scale, and here are the steps that we take to achieve this goal. So first, since we also don't have access to the entire Facebook and Twitter social network, we need to understand how to evaluate the reliability of these matching schemes in practice. And more precisely, we have to see how we can sample data sets for training and testing matching schemes that actually catch the hardness of the problem in practice. Then we can test the limits of current matching schemes, and finally we can see whether we can do something better. So to reason about these questions, we proposed a supporting framework which we called the ACID framework. And the key to this framework is to understand what does the reliability depend on. And why is this important? So understanding why the reliability depends on will allow us to see whether there is an opportunity for improvement in this matching scheme, but it also will allow us to understand how to sample data sets such that the reliability is not affected. So what does the reliability depend on? Of course, it depends on the features we are using to match the profiles. So the question is now how and what properties, attributes have that affect reliability. So we identify 4 properties an attribute should satisfy to guarantee a reliable matching: availability, consistency, non-impersonability, and discriminability. So first, to guarantee a reliable matching, an attribute should be available across social networks. So while my names have a high availability, I give my name in all these social networks. My bio has a lower availability, and I don't give my bio on Yelp or Flickr. And formally, we define availability by this probability, which kind of translates the intuition that I just gave you. Then an attribute should be consistent across different social networks. If an attribute is not consistent, then it will not help to match profiles. For example, here I have the same name across different social networks, but the location in each of my profiles is different. So in my case, location will be useless to match my profiles. And this is the formula for the consistency. Then an attribute should be highly discriminable. And this property is very important because even if an attribute has high availability and consistency, if it's not highly discriminable, it will not be helpful to match profiles in a reliable way. For example, here are 3 other accounts on Facebook that have exactly the same name as me. So my name alone will not allow to distinguish my matching profile. And an example of an attribute that is even less discriminable is gender. Half of the people are male, half are female. And we formalize discriminability as the property that there are non-matching profiles that have the same attribute value as the profile we want to match. Finally, this is a property specific to social networks, and ideally an attribute should be hard to impersonate. And I'm not sure if you are aware about the fact that impersonators indeed exist. So here is an example of fellow researchers at Princeton where someone that is not him created an account pretending to be him on Twitter. So formally, non-impersonability is defined in a similar way as the discriminability by this formula. So now we saw the properties, and how do these properties actually influence the reliability of a matching scheme? Well, we proved that the ACID properties are actually both necessary and sufficient to guarantee a reliable matching at 100% recall and 100% precision, and that we can also, in addition, we proved that the recall is very easily linked to the availability and consistency of an attribute, while we can give an upper bound on the precision we can achieve using an attribute by using the discriminability and impersonability of the attribute. So you can see that the ACID properties are nice because they separate well different properties we need in an attribute, and they are also able to determine the reliability we can hope to achieve when we do this matching. Now, the nice consequences of introducing these ACID properties is that it gives us ideas of how to sample dataset to evaluate the reliability of matching schemes. So far, people picked matching and random non-matching accounts and used it for their evaluation. And why is this not a good idea? Well, it's because this kind of sampling doesn't preserve the ACID properties that the original social network would have. And since the ACID properties influence the precision and the recall, then you will have a bad estimate of the reliability in practice. So I will not go into details, but we propose this reliability preserving sampling that keeps the ACID properties of the original social networks by sampling all the profiles in the target networks that are similar with the source profile. And we apply this technique and we gather data in real social networks to match Twitter to Facebook accounts, and we have about 1,000 matching accounts and more than 300,000 non-matching accounts. So if we take now the previous methods to match profile, and I'm just giving 2 examples, one based on SVM and one based on naive bias, and we train and test them using the reliability non-preserving dataset, what was previously done. So you can see that the matching scheme is able to achieve a very good precision and recall. You can see here that for a 95% precision, we actually are able to have a 90% recall, which is exactly what the studies were claiming in this paper. But now what happens if we evaluate these schemes over the reliability preserving sampling data set, which reflects the real difficulty of matching in practice. So you can see that the reliability it considerably decreases, and we can hardly match like 50% of these accounts, which is a big difference with what we believed before. Okay, so we saw that the reliability is very bad when we evaluate in real social networks, so we were wondering whether there is something better that we can do. And we tried different techniques to improve the accuracy of the SVM classifier and naive bias classifiers, and you can see more details about this in the paper. The second thing that we tried is to actually exploit some assumptions about the problem. And you know that in many social networks, users are not allowed to have more than one account. So we can exploit this, and instead of having a threshold on the similarity between two accounts, we just pick the most similar account, but only when it is much more similar than the rest of the accounts in the social networks. Again, you can see more details about this in the paper, and we call this new method the guard. So let's see how they perform. So by using this new technique, we were able to increase the recall, for example, using the guard to 29%. So this is good. It means that at least we can match 30% of Twitter accounts to their matching Facebook accounts, and that we were able to improve the recall by 100% compared to previous methods. But 30% still doesn't seem so much. So we're wondering if this is the absolute best that we can do. So to answer this question, we actually did this Amazon Mechanical Turk when we went and we asked human users to pinpoint the matching account. And human workers were only able to find the matching Facebook account for 40% of the Twitter profiles that we showed them. So what this shows is that, one, the matching accuracy we obtain automatically is not very far from what even humans can achieve. And secondly, if someone says that they can achieve a 90% recall for a 90% precision, it can be impossible because even humans are not able to achieve such high accuracy. So what you should take home from this talk is that existing schemes are not that reliable, and that services based on matching profiles are vulnerable to false matches. And second, that the ACID framework not only allowed us to improve the reliability of matching schemes, but more importantly, it allowed us to understand that there are some fundamental limits in matching profiles because the data set has so much discriminability that we can exploit there. Thank you, and I will take your questions now.
Okay, we have time for a couple questions.
What ideas would you have for future work on closing the gap between the 29% and the 40%?
I don't know, maybe better face recognition algorithms. That would maybe improve a little bit. So the problem is now that you have the data that you are using is public data. So generally people don't have many photos that are public. Usually have only the profile, one picture of the guy. And then you have to decide only based on what these two photos, whether they portray the same person or not. And currently the algorithms are not very good at this.
What was any kind of face recognition in your algorithm?
So we use photo matching, whether we detected whether there is the same photo or not. We tried face recognition, and it didn't. I mean, we were not able. They were not very accurate, so it didn't change the results.
Okay.
Okay, and we have time for one more question.
Hi, you mentioned impersonation among the types of things that you were considering. Which can you give an example of one characteristic that is difficult to impersonate? Because on the things that you show, I can take your picture, I can take your name, I can take.
Yeah, I would say that friends is the hardest to impersonate, because you might have links to some of them, but you cannot have links to all the friends of someone.
Okay, well, let's thank the speaker again.